Okay, so in this lecture, we're going to begin to discuss a series of separation techniques, which is essentially the theme of Unit 2. So in this course, we're going to talk about when you have a mixture of various compounds in solution, what different methods are for separating those compounds. Um, and sort of the simplest, and the starting point here, the simplest separation is a liquid-liquid extraction. And this will function as a separation of solutes in either aqueous or organic solvents. So let's review a few concepts regarding solvation. As I mentioned, the goal of this compound is always to separate molecules A, B, and C, for example, from one another. So if you have some complex mixture of molecules, we can take advantage of different solubilities based on the varying properties of compounds in solution. And what you should recall is that like dissolves like, or compounds that exhibit similar polarities are likely to mix together. So polar compounds are going to favorably interact with polar solvents, and nonpolar compounds will more readily dissolve and interact with nonpolar solvents. So what we're going to do during a liquid-liquid extraction is we'll use a device known as a separatory funnel. And that separatory funnel will contain two separate phases. One will be an aqueous phase, and one will be an organic solvent. So these two solvents are going to be used because they have very different polarities. The organic compound is going to be nonpolar, or at least much less polar than the aqueous or the solution with a bunch of water in it. All right, polar solvents are said to have very high dielectric values. Epsilon, that's a measure of how polar they are and how well they stabilize charge. Nonpolar solvents are going to have low dielectric values. So these two solvents of vastly different polarities are said to be immiscible, or these two solvents will not mix at room temperature. So let me go through some examples of various solvents that are used. The common organic solvents are going to take on some molecular formula CX, X number of carbons, and Y number of hydrogens, so hydrocarbons, such as hexane or benzene. Other common organic solvents include ethers, such as diethyl ether, or you can have halogenated solvents that are also fairly nonpolar and organic, including tetrachloromethane or dichloromethane. Okay, so I'll keep with the color scheme here and show you that these are the organic or mostly nonpolar solvents that have low dielectric constants. And all of these nonpolar solvents have the common theme of a vast number of carbon-carbon sigma bonds and carbon-hydrogen sigma bonds in their structure, right? And recall that the electronegativity of carbon is equal to the electronegativity of hydrogen, approximately. So what that means is these CC and CH bonds are generally nonpolar. or there are no partial charges or permanent bond dipoles within these structures. Now, introduction of a halogen such as chloride or an oxygen, those do induce slight bond dipoles. But for the most part, compared to water, these are still very nonpolar. So when you're putting two different immiscible liquids into a separatory funnel, one of them will sit at the top and one will sit at the bottom. There'll be two distinct layers. And the top layer is always going to be the solvent of lower density, while the bottom layer is the solvent with a higher density. Generally, the aqueous layer is going to be more dense than the organic, but that's not always true. There are some exceptions. However, you'll be given the densities if you're asked to determine what's at the top versus bottom layer of this separatory funnel. So when we put a solute, or we have a mixture of solutes in a solvent, that solute can undergo partitioning if there are two immiscible liquids that are in contact. And partitioning is just the solvation of some solute in both phases, the aqueous and organic. And this solvation is going to reach equilibrium. Where that equilibrium constant is the partition equilibrium constant, Kpart. So when a solute is allowed to exchange or be solvated in both phases and there's an equilibrium process, this is partitioning. So if we think about compound X and we're extracting it into diethyl ether, so this is our shorthand for diethyl ether, it's the organic phase. We have aqueous X, which means X is initially dissolved in water, and we add diethyl ether to that aqueous solution. Then X, which is originally aqueous, can come in contact with the organic solvent and then interact with the ether molecules or the organic. And Kpart, in terms of concentration, it's just like any other equilibrium constant, where solute X in the organic layer divided by solute X in the aqueous layer, the ratio of those concentrations is a unitless constant that will tell you about the number of molecules in each phase. So another more explicit definition of Kpart is not just writing these bracket notations for concentration of X, but we can also write it as the moles of X that are soluble in the organic layer divided by the volume of the organic layer over the moles of X soluble in the aqueous layer over the volume of the aqueous layer. Okay. So if for some reason you use equal volumes of organic solvent and aqueous solvent, then Kpart will simplify to the mole ratio, moles of X organic over moles of X aqueous. That's only if the volumes are equal. So if compound X is very polar, then it's going to primarily be in the aqueous layer, or the concentration of aqueous will be large, the denominator is large, and thus it will be a fraction, or Kpart will be between 0 and 1. If X is very nonpolar, then X is going to prefer the organic phase. Like dissolves like. And then the concentration of X in the organic phase would be large. So Kpart would be greater than 1. And if X is equally soluble, okay, or if it has sort of an intermediate polarity, where it enjoys both very polar aqueous phase and the nonpolar ether or organic phase, then you would expect that the concentration of X in the organic would be approximately equal to that in the aqueous layer, and Kpart would be 1. So Kpart tells us about the relative affinity of a compound based on its polarity for each of these two phases in your separatory funnel. Tells you how much it enjoys spending time or being solvated in a nonpolar organic solvent as opposed to a polar aqueous solvent. Okay. So I wanted to go through and look more at a sort of pictorial representation of what's going on when we do a liquid-liquid extraction. So I'll sketch here the separatory funnel, and the separatory funnel generally is going to be containing an organic layer on top, assuming the organic is less dense. I'm sketching that here. And then an aqueous layer on the bottom. And it will be sitting upright on the benchtop. And this is assuming, once again, the density of the aqueous is greater than the density of the organic. And if we start out with aqueous compound X, let's say we have 5 molecules of X in that given volume of aqueous layer, or 5 moles, however you'd like to interpret it. If we take this and we stopper it, shake it well to allow for equilibration, and then we wait for the compound to settle out at a constant concentration in each phase, what we're going to observe is this change. Some of the molecules of X are going to exit the aqueous phase and enter the organic phase. And this equilibration continues. X molecules from water continue to go to the organic phase, and X molecules from organic continue to go back to water. This reaches an equilibrium, or a partitioning constant is reached. So Kpart, which we said was the concentration of X in the organic over aqueous, here is 4:1, as I've shown. That's assuming the organic volume is equal to the aqueous volume. If it's not, then it's not simply a mole ratio. But here, if those volumes are equal, there are 4 molecules of X at equilibrium in the organic phase and 1 molecule of X in the aqueous phase. So because Kpart is greater than 1, that indicates that X prefers the organic phase, or X is probably fairly nonpolar. It's more similar to the polarity of the ether, the organic phase, than it is to the water. So when you're doing math problems with extractions, there's one very important equation you must understand and be able to apply. And it tells us about the fraction of X, Q sub X, that remains in the original solution. So Q is the fraction of X molecules remaining in the original phase, I'll say phase 1, after n number of extractions are performed. Now, generally speaking, the aqueous solution originates with the solutenant and the organic solvent is pure. Or in other words, we can apply these terms of phase 2, the pure liquid that we are extracting the nonpolar X with, or phase 1, which was the aqueous mixture. It's the original phase in which X belongs. Okay, so assuming that it goes from phase 1 to phase 2, or aqueous to organic, then the fraction remaining in phase 1 is equal to the volume of phase 1 over the volume of phase 1 plus the partition coefficient multiplied by the volume of phase 2. Okay, so in this example here, I was assuming, because of this 4-to-1 mole ratio being the partition coefficient, that the volumes were equal. So the mole ratio was simply the ratio of the molarities. So this equation here is unitless, okay? It's a volume divided by another volume term, and Q will always be the fraction between 0 and 1 that can tell us the percentage of X remaining in phase 1 after we perform some n number of extractions. Now this n value must be an integer. You can either perform 1 extraction or 2, but you cannot do 1.2 or a partial extraction. So in the case where the diethyl ether, phase 2, and water volume are equal, then the Q equation is going to simplify. And the fraction of X remaining in the original phase, we can write now as V1 over V1 plus Kpart times V1. All these terms have V1, so I can pull that out and say it's V1 over V1 multiplied by 1 over 1 plus Kpart. Of course, V1 over V1 cancels, and we can now say if the aqueous and organic volumes were equal, then Q simplifies to 1 over 1 plus Kpart, all raised to n number of extractions. So let's think about how this general equation for Q, or the fraction of X remaining in the original phase, depends on a few of these variables. First of all, it depends on the number of extractions n. Okay, so what you'll see is that this is always a fraction here because it's volume 1 over that same amount plus something. In other words, we're always raising a fraction to the power n. And raising a fraction to an integer exponent is going to cause a decrease in Q exponentially with an increase in the number of extractions n. If we increase the volume of water, V1, right, then we'll see that that's going to increase on the top proportionally with the bottom, okay? And increasing the volume is going to allow a larger number of moles of solute to remain in the aqueous layer. And that means we're going to increase the amount that we retain or increase the fraction moles of X remaining in the water. So because the partition coefficient is a constant, it says the ratio of concentrations of X in the organic and aqueous layer are going to be at a fixed value. So adding more water allows a larger number of moles of X to remain in the water. If you are to increase the amount of ether that you're extracting X with, then more of the X will come into the ether phase, or will decrease Q. There will be less or a smaller fraction remaining in the original phase. And if you increase the partition coefficient, that means we're going to increase the amount of X in the organic phase. Remember, Kpart defined here, right, was the 4 moles of X organic over 1 mole aqueous in those equal volume layers. So having a larger partition coefficient means it's going to be more soluble in phase 2, or the phase that is entering. That will increase the amount of X in the organic layer, decrease the amount of X in the aqueous layer, or decrease Q. Okay. So we will do some math problems with these equations for liquid-liquid extractions in a subsequent video. But for more practice with the theory and concepts behind separations and liquid-liquid extractions in general, you can visit Unit 2 of my analytical course guide at chemguides.com.